it transmits to the receiver, and Jm is the midpoint of the transmitter and the receiver, and Rm is the distance between the transmitter and Jm, and the Jm is the distance between the receiver and Jm, the distance is Rs, and the red line is the line for the reflected ray, and the black one is for the diffracted ray. And as I told you, the PLR is the path loss encountered by all rays reflected on the surrounding, and PLD is the path loss encountered by the rays diffracted on the corner at the intersection. And we add these two components, which is the path loss, which is PL is 10 log 10 PLD by 10 plus 10 log 10 to the power PLR by 10. Formula application. NLOS2. If the two vehicles are in NLOS2, then the total path is a combination of 4 components. One is like completely due to reflections, one is completely due to refractions, and one is like first it's reflected and then diffracted. The other one is first it is diffracted and then reflected, which is nothing but PL equals 10 log 10 PLDD by 10 plus 10 PLDR by 10 plus 10 to the power PLRD by 10 plus 10 to the power PLR by 10. This is the diagram, and Tx is the transmitter and Rx is the receiver, and there are two midpoints, which is Jm and Jp, and the Rm is the distance between the transmitter and the midpoint, and Rs is the distance between the Jm and Jp, and Rd is the difference between the distance between the Jp and Rj. And these color combinations, the blue color is for the reflection and then diffraction, and red color is for the diffraction, and black color is for the reflection, and purple color is for the diffraction and reflection. Sample propagation. We just consider a transmitter. We consider a grid network where this is the transmitter and the receiver is moved from the transmitter in the line of sight, and then it becomes a non-line of sight 1, and then it becomes non-line of sight 2. So we take this example to do some experiments, and we draw a graph based on the locations, and we see that the path reduces for LOS, and then it still reduces for NLOS, and it still reduces for NLOS2. And this is one more diagram which explains us clearly that the corners which are blue in color has most attenuation compared to the straight lines. Then we do the connectivity experiments. So in this connectivity experiments, we do experiments for fixed to mobile and mobile to mobile. So in both these setups, the nodes are periodically broadcasting a packet containing their geographical coordinates and the GPS timestamp. Then the frequency of the transmission has been set to 10 packets per second. In fixed to mobile, we performed two different tests, with one car revolving around a block and the other fixed, first in the middle of the block and then at the intersection, as shown in this diagram. Here the fixed car is in the middle of the block and the second one is in the intersection. And the blue color is the simulation and the yellow one is the real experiment in both the cases. So in both experiments, the fixed car periodically sends out broadcast packets. The mobile car then saves the geographical coordinates where it received each packet. And we also do the experiment for mobile to mobile, and in this case the two cars will be revolving in opposite directions, and one of the cars would store the position it received the packet at, together with the position of the other car included inside the packet. So each signal received packet is represented as a red line, and the receiving and sending positions represented by blue squares as shown in this figure. And since we did the field experiment and the simulation, they look similar. And we find the link quality. To find the link quality between the transmitter and the receiver, there are two experiments which we did. These are the experiments. The source, the receiver will be moved away from the source in these positions. The source is right here, and the receiver is moved from position 1, 2, 3, 4 in the line of sight, and then a corner. Then in the second experiment, the source is there, and the first one is a line of sight, and then the rest are towards the corner. So, and the link quality is defined as the number of packets received divided by the number of packets sent. And we do this experiment, and if we plot a graph, the corner with the we plot a graph comparing this corner with other flat propagation models, corner with Rice and corner with Raleigh. According to this graph, we find that Rice is poor and Raleigh does a much better job than Rice. In Vanit simulation, to evaluate the difference between the corner and the flat propagation models, we use the Vergilius trace analyzer, which extracts the relevant network metrics from mobility traces. So these are the 4 different metrics which the Vergilius trace analyzer calculates for the corner and other 2 flat propagation models, and we figure out which one is better. So connectivity index is a measure of how well the network is connected. So it depends on, it has a value of 0 to 1, and if it is 1, then it is fully connected. Then average hop represents